So, and no one gets thrown out ever. Okay, that's still fun.
Oh, there it is.
Steven Blue.
Not bad.
That has to be good.
Yes.
Hey everyone, we're going to finish 5.1 today and start 5.3. So we'll start with the this warm-up problem. I'll put this on a separate sheet just to give myself more space as well. So here's the problem. We're going to find the derivative and then plug in the x value. And Friday we talked about how we can expand natural log problems to the point where our derivative rule will be manageable and easy to apply rather than having to deal with messier quotient chain product rules. Okay, so we're going to mainly approach it from involving this natural log of u equals u prime over u. But first, if I want to find the derivative, do you notice any method that we have to involve here? Yeah, for the x squared. But what about from a larger perspective here? Yeah, product and a little bit of chain within here, but really it's two functions, right? You got the x squared, you got the natural log. They're being multiplied. We got to go through product rule. Okay, so let me set up product rule here. Okay, so let's go through this piece by piece here. F prime is 2x. G function, no changes. Back to F. And then natural log of g of x, we're going to use this rule here. So how would you apply natural log of g of x using natural log of u's derivative?
So it would just be g prime over g.
Yeah, g prime over g. We can't find the derivative from a numerical perspective of g of x, so the best we can do is leave it in function notation and just call it g prime. So g prime over g. Okay, so that's our derivative. Now we can move on to giving it a specific value. Replace every x with 2. All right, so I'm going to try to clean this up here. What can I replace g of 2 with? Anything given to us? Yeah. Replace g prime of 2 with -4. Yeah, yeah. Clean this up. I replace, this should be 3, 4 natural log of 3. All right, as far as we can go here. Okay, let's move into today's topic, which is log differentiation. Okay. Anybody still need this page? All right, so today we're going to talk about log differentiation, which is still using log rules, but it's the second part of 5.1. So again, on Friday, we talked about how we're asked to find the derivative of all these natural log problems, but we always look to see if there's a way to expand. Because we know that if we can take advantage of these expansion properties, our derivative, I mean, we may have more derivative problems to find, or more terms to find derivatives, but each of them will be easier, right? They're all going to be a little bit more manageable than one large complex problem. So it's nice having these properties, right? These properties kind of allows us to break up a problem into smaller parts. So today, with log differentiation, it's the idea of taking a non-log function and applying log properties so that we can expand before differentiating. So what we're going to do is we're going to introduce natural logs into the problem so that we can take advantage of log properties. Okay, so that's going to be the goal that we're going to apply. So here are the steps. We're going to take the natural log of both sides of the equation. That's so that we can get it ready for log properties that we want to use. Then we're going to expand using log properties on the right side. Once we have that, then we're going to use implicit differentiation on the left side because the y is no longer by itself. It's going to be part of a natural log expression. But then we can expand the right side, find the derivative, and then solve for dy dx. Okay, so let's look at example 1 and see if these steps make sense. So we look at this problem here. We do have previous rules available to us, right? We don't have to use log differentiation. But the advantage of log differentiation is so that we can avoid having to deal with a combination of, in this case, chain and quotient rule. So first step, we're going to take the natural log of both sides. Now the right side, we have some properties that we can use. So do you see a property that can be applied on the right side here?
Quotient property?
Yeah, quotient property. Maybe there are some other ones, but I think we want to start with the most obvious one, right? The one that we see affects the largest portion of the problem. So I'm going to use the quotient property. So I'm going to treat the numerator as my a, treat the denominator as my b, and just make it natural log of a minus natural log of b. And so the whole point of it is we want to expand this out so that the derivative will be easier down the road. And while I'm at it, I'm going to go ahead and convert that radical to a rational exponent just to get ready for my next step. So already it looks easier than what we had before. Okay, but we can keep going, right? Do you see what else can we do to make this even easier to work with?
the exponent.
Yeah, let's bring those exponents down, right? This is not derivative process. This is simply power property. Bring that exponent down. Anytime we can bring an exponent down, it'll just make things easier from our derivative standpoint. Okay, questions so far? Now, it's a lot easier because the only rule we have to apply for each of these terms is just, they're all just u prime over u. Right? Now, the left side, I know looks a little bit involved here because we have that y, but we're just going to apply the derivative rule the same way that we would x's. So instead of 1 over x, it's now going to be 1 over y. But we just took y's derivative, so we also need to have that dy dx. So basically, when you do log differentiation, the left side is always going to be this. It's always going to turn out to be 1 over y dy dx. Okay, right side. The 2 is the coefficient. That's not going to go anywhere. What's the derivative of natural log of x minus 2?
1 over x minus 2.
Yeah, u prime over u. We simply take the derivative of whatever is inside the parentheses, put it up top, and then we copy the exact parentheses below. One half coefficient stays. U prime over u for my second natural log is
2x over x squared plus 1.
Yeah. Again, notice that when you find the derivative of natural log, there's no more natural log notation in our derivative, right? It's just u prime over u. It's not natural log of u prime over u. Okay. So all we're doing is we're just following the rule, right? We don't want to try to. We don't have to be creative and come up with anything unique. We're just following whatever the rule says. Okay, so this ends the derivative process. We just have to solve for dy dx then. Okay, questions so far? Okay, so doing a little bit of cleanup here. I can take out one of the 2's. I'll bring the I'm going to multiply both sides by y because I want to solve for dy dx. So the y is going to be shifted over to the right side of the equation. Dy dx represents my derivative function. Okay, so we basically have the derivative, but we're going to make one final substitution. We're going to find a way to replace y. And we can always replace y with the original equation here. Okay, because that's what y is equal to. Because we started our equation as a function, we should be able to represent our derivative without any involvement with y's. So our derivative should be, as messy as it is, we should be able to represent everything in terms of x, because it's still a function. So you're going to notice that with log differentiation, your derivative is going to look a little messier, but I'm not going to ask you to clean it up. If you leave it as one sprawling derivative, that's fine. Okay, any questions so far? Okay, let me recap the process. We start off with something that looks a little bit complex. So we involve natural log on both sides. Once we have natural log in the expression, we expand using log properties. Once we expand it all the way, it's just a matter of applying u prime over u for each of the terms. Once we find the derivative, we bring the y over to the right side, and then replace the y back in terms of x. Something I do want to point out is we only do log differentiation if there is no logs to begin with in the problem. If there's already natural log in the equation, then we can jump directly to log properties. We don't want to do log differentiation for log problems because then we're adding another layer of natural log, and that's just going to make things more complex. All right, so we only want to do log differentiation when there's no logs in the equation, so that we can introduce logs so that we can take advantage of the properties. But if there's already logs in the problem, then we should be able to jump directly into the properties without having to do any additional adding of any element. Okay, any questions with one? Okay, log differentiation kind of falls under two categories. We have one category of problem where it's not the only way to find the derivative. We have other methods, right? We could go through quotient, chain, other rules. It's just that sometimes with log differentiation, we can avoid complex rules by taking advantage of log properties. So that's one form where it's an easier process for certain problems, okay? The other use of log differentiation is for problems where we have no choice but to use log differentiation, where we just don't have an explicit rule to handle the derivative of whatever form is given to us. So this is a variable raised to a variable. We don't have a rule for variable raised to a variable. We have power rule, which is a variable raised to a constant, which we can do. The next section, we're going to learn about exponential functions, which is a constant raised to a variable, which we can also do, but we don't have a rule for a variable raised to a variable. So the workaround is log differentiation, because if we can make it a part of a log equation, we can bring that exponent down, and when that exponent comes down, using power property, we will then have a lot more options available in terms of algebraic methods. It's just sitting up as exponents, we just have less options, less availability to algebraically solve equations without getting really messy. So we're going to take natural log of both sides and see where that leads. And I just thought of this today, where I think maybe this is helpful. Put your exponent in a set of parentheses, because when it comes down, sometimes that +3 can get lost. We want to just make sure we understand that the 2x plus 3 is a unit. It's going to stay together. Okay, we took the natural log of both sides. We see, is there any property that we can apply? And we see this third property, right? We can bring that exponent down in front. It makes it easier to manage. And now we can think about the derivative step, right? There's nothing more to expand. The left side is always going to be the same. It's always going to be 1 over y dy dx. But the right side, in this case, what do you think we have to involve here if we want to find the derivative? How many expressions do you see?
Oh, product.
Product rule, yeah. Okay, what's my g prime going to be?
2. Or 1 over x.
No, 1 over x. Okay. Our final thing that we can do is bring that y over to the right side. replace the y back in terms of x of the original equation. And don't worry about having to clean anything up. If you just leave it all as one big mess, that's okay. Okay, so I see a replacement for y, which is just my original equation. Okay, any questions with log differentiation? Any questions about the process with the steps? So I think I want to skip over the curve sketching. We'll come back to this. This is kind of a extended problem. Maybe we can get to it when we are in one of the review days. But I want to go over a new topic today, another new topic today, which is inverse functions. So if we can turn to the next page. So this topic is inverse functions and or derivatives of inverse functions, but I'm going to review inverse functions first. So a function and its inverse, their x's and y's are going to be swapped. So any order pair on one function, there's going to be that same number, but then just in the x's are y's and y's are x's now. Which means that if all my order pairs are flip-flop, then my domain and range is also going to be swapped. Graphs are always going to be symmetric over the line y equals x. So don't draw this yet. We'll do this a little bit later. But something like this, right, where if you can visualize a graph being folded over the line y equals x, this diagonal line, then you know you have a function and its inverse, right? You're always going to be able to take a function and its inverse and kind of fold it across that diagonal line and make it overlap each other. A function must be one-to-one, meaning that it must pass the horizontal line test in order for its inverse to be a function. So for instance, a parabola is a function, right? But its inverse is not going to be a function. And a quick way to tell is the fact that it doesn't pass the horizontal line test. So that means that once we flip it to its side and make it into its inverse, we see that it's not going to pass the vertical line test. So unless a graph passes the horizontal line test, we know that its inverse is not going to be a function. So in order to guarantee that, a function must be monotonic, which means that it's always increasing or decreasing. Okay, so if a function is always increasing or decreasing, maybe the graph looks something like this. This will pass the horizontal line test, right? I'm only going to touch one point no matter where I draw my horizontal line. But once I flip it to its side, it's guaranteed to must pass the vertical line test. So the function is always rising or always falling, then we know that its inverse is going to remain a function. Okay, so we're going to practice first some review in terms of finding an inverse of a function. So here are the steps for finding inverse. First step is we're going to switch the x and y's. Swap or switch x and y's. So wherever you see a y, replace with an x. Wherever you see an x, replace with a y. Second is you want to solve for the new y. Okay, so let's practice finding inverse of a function. So f of x is the same thing as y, right? So I can say y is equal to 6x plus 2. That's my starting equation. So if I were to swap the x and y, what would that look like?
X is equal to 6, y plus 2.
Yeah. Now, when you swap your x and y, you're not going to move anything else, right? So the 6 is not going to go along over to the y side. Okay, so x equals 6y plus 2. We're just taking the variables, picking them up, and making them switch to another variable. Okay, so now I want to solve for y. Divide both sides by 6. And now we want to find the inverse. We want the notation. We have the inverse function. Let's just write that as a notation. So f inverse of x. Okay. We're going to skip example 5, but I want to use this space to demonstrate visually what we're going to be trying to, what the relationship is with the derivative side of things. Okay. So let's start with this. If you guys can draw this along with me here. So I'm going to draw a picture of a function and its inverse. Again, we know visually we're looking at a function and its inverse. If you can imagine folding the graph across this diagonal line and imagining that the graphs will overlap. So we can kind of imagine that, right? This, if you fold this over the line, you can kind of imagine it kind of overlapping. So I'm going to call the top one f of x and the one below as f inverse of x. Okay, I want to give an example of, in terms of the slope. There's a relationship between the slope of these two graphs, but I'm going to start with order pairs. Let's say there's an order pair that sits on the function, on the original function as 1, 4. So if there's an order pair that is 1, 4 on the function, guess what order pair has to live on its inverse function?
Negative 4, 1.
All we do is, yeah, just swap the x and y. So just 4, 1, right? So here you can kind of imagine this 1, 2, 3, 4, 4, 1. Okay, so obviously these are different points on the graph, but we call these corresponding, or I call them corresponding points because they're kind of related to each other in the sense that their x's and y's are flip-flop. But from the derivative side of things, there's also a relationship at these 2 points of these 2 separate functions, the slope values. So there's a numerical relationship in terms of their slope values. So I want us to explore that. Okay. What does the slope look like to you? Positive or negative? Positive. Steep or gradual? Pretty steep. Okay, so let's say it ends up being slope of 7. Okay, just for demonstration purposes. Let's say that's a slope of 7. Now, this slope, I'm going to draw a tangent line here. Positive or negative slope?
Also
Also positive. Steep or gradual? Very gradual, right? It's not going to be a very steep. So obviously this is not going to be 7, right? That's not a 7 slope. But the relationship is that this slope is going to be the reciprocal of that number. So the slope is going to be 1, 7. And that's what we're exploring today for these problems. We're going to be doing most of our work on the function side of things. We're going to try to figure out what the slope is using derivative, using power rule, using methods that we know. And then once we find this number, we can turn around and conclude what the slope of the inverse function at its corresponding point. Okay, but I want to start with a visual so that it won't just feel like a bunch of symbols, right? You can kind of convince yourself that this makes sense, right? The steepness values make sense. Okay, so I like to organize my information from a order pair standpoint and also from a derivative slope standpoint. So my order pair information, I like to put it at the top spaces, and then the bottom spaces, I like to organize it from a derivative standpoint or slope standpoint. So a lot of these problems, we're going to kind of go through it from this angle here. The problem is always going to ask you, what is the slope of the inverse at a specific point? So it may ask you, find the inverse, the slope of the inverse at, let's say, 4. But really, the problem is not going to give us any information about the inverse function. It's just going to give us the fact that the x value is 4. So I'm going to create a space for my order pairs, for my inverse and my original function. I don't know what the y value of my inverse, but I do know the x value of my inverse. But if 4 is the x value of my inverse, then 4 must be the what? Of the y value of my original function. So the way that we're going to start off the problem that we're going to see is whatever number they give you, it's going to be on the inverse side of things. But everything that they give us is going to be on the function side of things. So basically, whatever they give you in the problem, just understand that number is the y value of the original function. And we're going to have to kind of do a little bit of solving to figure out the x value. So let's say we plugged in 4 and for y. We went through the process, which we're going to do with these examples. Let's solve for x. And when we solve for x, we get 1. And I really don't need to fill this out, but I like to just see that symmetry there, that a function and inverse, I see the flipped order pairs. And then once I have this information, I'm going to work my way to figure out f prime of 1. So a lot of times it's just power rule, whatever the function is, we find the derivative, find the slope, figure out what the slope value is, and then we turn around and we make our final conclusion, and that's our answer. So we're just going to kind of make our way around this chart. Whatever x value they give you, you know is the y value of the function. Work to figure out what the x value is so that when you find the derivative, you can actually find the slope. And then once you find the slope, just flip it, and that's going to be the answer of the slope of the inverse. Yes?
So, Mr. Yang, for those type of problems, will you be given the original function and you'll have to find those values based off of that?
Exactly. So all these problems, well, most of these problems, you're going to get the x value, which is really disguised as the y value of the function. And then everything else is going to be on the function side. So take this, find the x value, find the derivative, and then all your work is going to be on this side, and then you're going to make the final conclusion of this. Okay, so I know right now it's kind of abstract, right? I haven't done an example yet, but I want to kind of just map out the steps with you, and then we can look at it in detail. So here's example 6. We're trying to find the slope of f inverse at -3. So that looks like an x value, but it's really disguised as a y value of the original function. So we'll just keep that in mind. So my ultimate goal is to figure out the slope of f inverse at -3, but I don't have any information on inverse function except for the fact that the x value is -3. Okay, I know my order pair is going to be something like this. But everything that we have available is in terms of f. So this -3 is really the what of the f function? The y value. Okay, y value. So I'm going to say f of whatever x value is going to be -3. So I'm going to work backwards here. I'm going to put -3 in for the y position and see if I can work backwards to solve for x. I'm going to bring the -3 over, add 3 to both sides. Now we're going to see with some of these problems is that it's not factorable, which means that we can't solve this going through factoring method. We can't do quadratic formula. So we're going to go through guess and check. I know that sounds tedious, that sounds inefficient, but for these guess and check problems, it'll be an easy value. It'll be numbers around 0. So if you test 0, if it doesn't work, then try 1. If 1 doesn't work, then try -1. That doesn't work, then try 2. That doesn't work, try -2. So once you've tried those options, one of those will be the value that works. So we're just going to go through guess and check here. 0, the 0 work? 0 plus 0 minus 5, is that equal to 0? No. Okay. How about 1? Oh, I'm sorry. Plus 5. Sorry. I should have added 5 to both sides here. So I added 3 to both sides, make it 5. Okay, so does 1 work? 1 plus 4 plus 5 doesn't equal to 0, right? Okay, so we know that's out. How about -1? -1 minus 4 is -5. -5 plus 5 is 0. Okay, so we know -1 works. So we have our x value, which is what we need. I'm going to put this, balance it out. So now we have -1, which is helpful because if I can figure out f prime of -1, then that's all I need to get to make my final conclusion. So how can I work my way to find f prime of -1? Find the derivative first, right? Then we can plug in the -1. So let's find f prime of x. What's the derivative?
3x squared plus 1.
Yeah, power rule, right? Easy. We have the slope formula. We have the x value to evaluate. So the slope of the f graph ends up being what?
7.
So if my slope of the f graph is 7, then the slope of the inverse must be 1/7. That's our answer. Okay, so all these problems are going to kind of follow that initial step. Whatever number they give you, it's really the y value of the original function. That number, put it into the y position of your function, solve for x. Once you solve for x, then you have a number that is available for you to evaluate the derivative. So find the derivative of f, plug in that number that you just found, find the slope, and then flip that slope to get to your slope of the inverse. Okay, let's try example 7. I'm going to need a little bit more room, so I'm going to put this on a separate sheet here. So find the derivative of f inverse at 1. Here's my chart. Help me organize my information. My order pair on the f inverse side of things. But we know that the 1 is really a disguise for the y value, right? So I know that it's going to be f of some x value being equal to 1. So take whatever number they give you, put it in the y position of your function. Now this one is a little bit more manageable. We don't have to go through guess and check. I think we can solve this by hand here. Square both sides. Okay, add 7 to both sides. Take the cube root. So I know the x value, which is going to be useful because now my next goal is to figure out f prime of 2. And that will lead me directly to the slope I'm after. Okay, so if I want to find f prime of 2, I first need to find f prime of x. To find f prime of x, what do you think we need to use here to find the chain rule? Yeah, got a function within the function here. So outside versus inside. Outside's derivative.
1/2.
Mm-hmm.
Negative 1/2.
Good. Keep the inside intact. Multiply by the inside's derivative. 3x squared. Okay, I'm going to do a little bit of cleanup with my f prime, and then we can work into 2. All right, so there's my cleaned up derivative. I'm going to find the slope of the f graph at 2. Three times 4, that's 12. 8 minus 7 is 1. Square root of 1 is still 1. 1 times 2 is 2. So my slope ends up being just what? 6. So if my slope of the f side of things is 6, then the slope of my inverse side is going to be 1/6. Notice all of the work that we did is on the f side of things because that's what we have. And then we just have to take one final step, just being able to understand that the slope that we're after is the reciprocal on the sitting on the other graph. Okay, any questions? All right, let's look at the next two. I think these two will be easier because we just have to put we just have to put all the pieces in place. We don't really have to do any steps in terms of working out calculus steps. Just have to kind of put pieces in the right place. So let's look at example 8. Oh, does anybody still need this? Guys, okay? Okay, let's look at example 8. Instead of f and f inverse, they're saying that g and f are inverses of each other. So whenever you see g of f of x equals x or f of g of x equals x, that's just establishing that that the two functions are inverses of each other. Okay, we're trying to find f prime of 2. So I'm going to put f prime of 2 down here. So I know there's an order pair that exists on the f side of things, but where's that 2 going to live on my g graph?
On the y.
on the y side, right? So I know that I have this figured out so far, right? So this is what I can gather just from what I know between f and g. Okay, do we have anything that matches this? Do we have an ordered pair where g of something is equal to 2?
It's 7.
Yeah. So we can put that piece in, right? So if g of 7 equals 2, I know f of 2 is equal to 7. Okay, I'm going to get that that relationship there between the numeric values for my ordered pair. So then if I have 7, that's good, right? Because if I can find g prime of 7, then that will help lead me to what I'm looking for, which is f prime of 2. Okay, what's g prime of 7? Okay, that's given to us as well, right? So if g prime of 7 is 10, then f prime of 2 must be, that's it. Okay, can you guys try example 9? I think it's going to be a similar problem there. Try 9. All right, what'd you guys get for your answer?
Negative
1, 4. Okay, so we know that the 3 that's given to us is really the y value of my g function. So I have this as my starting point. And to fill in the gap, I know they tell us g of 9 is equal to 3. So if I can find g prime of 9, then the slope of the g graph is going to be linked with the slope of the f graph at 3. So g prime of 9 is negative 4. I know the slope of my f is always going to be the reciprocal. Don't change the sign, just flip and make the reciprocal. All right, questions? Okay, so we finished basically 5.3. We can start 5.4 tomorrow, I think, which is good because we probably need some time to kind of review. A lot of things from chapter 2 is going to keep coming back. All right, if you're on Teams, have a great day. See you guys tomorrow.
Thank you.
Thank you.